Welcome back, and I've got another brilliant experiment to show you today. It's a really important experiment in the history of physics. What we're going to look at is the charge-to-mass ratio of the electron. So I'm going to show you how to work out the charge-to-mass ratio of an electron at the end of the video. I normally don't have any maths at all in my videos, very purposefully, so you can just get a feel for the physics. But if you want to hold on to the end of the video, I will do a calculation to show you what this apparatus gives for the charge-to-mass ratio of the electron. So to do this experiment, what we need to do is we need to swing an electron into a circular motion. So I've got my Electron tube here, and it's slightly different from the ones you might have seen earlier in my videos. This one has two electron guns, but the gun we're going to use is one that points vertically upwards. And what we then are going to do is deflect that beam with a magnetic field going through the tube into a circular motion around the inside of the tube. And because there's a low pressure gas in here, we'll get some ionization, so we'll be able to see that beam glowing slightly green. So let's wire up our vertical electron gun. And you've heard me say before that my physics teacher always taught me, wire everything up in front of your students. So here we go for the filament, 6.3 volts at about 2 amps. And I need to select the filament to the vertical electron gun. So there we go, that's that one. That's going to get nice and hot, and electrons are going to come off its surface, or maybe it's going to heat a cathode. So let's make it very negative, and we'll repel the electrons off it. So there we go. In this case, to about 150 volts. And our anode is over here, so we'll connect to our anode. And 150 volts. So let's now turn this on and see if we can see the short length of vertical electron beam in this tube. Okay, so I've darkened the room. I'll turn on the power supply. There we go. And we'll just wait for the heater to heat up a little bit. I can just begin to see it glowing orange there. And then I'll turn up the accelerating voltage to about 150 volts. And there you go. I hope you can see that on the camera, but I'll do a close-up. There's our vertical beam, and what we're now going to do is put a magnetic field through the tube between the camera and me, and we're going to deflect that beam into a circular path. So the next thing we've got to do is create the magnetic field that runs through the tube. And if you think about it, the electron beam's going this way. We've got the magnetic field going through the tube, and you can use left-hand rules and things, but now's not the time for that. And we can bend the beam at 90 degrees to that. So to do that, we're going to use some Helmholtz coils. And these have the advantage of giving a fairly uniform field if we wire them up properly. So there's one coil, and here's the other, and also you can see through them, so you can see the beam quite nicely. So to get a magnetic field, we need to come into the Helmholtz coil from a low voltage power supply, and we need about 2 amps flowing through these or thereabouts. Out of that one, into the next coil, and back to the power supply. So quite a complicated arrangement here, 6.3 volts for the filament heater, 150 volts for the accelerating anode, and finally a separate DC power supply giving us a low voltage but a reasonable current to get these coils to become magnetic. So let's turn it on, and then I'll turn up the magnetic field and watch what happens to our vertical beam. So back in the dark room, let's turn on the power supply to the electron gun. So firstly, I'm turning on the heater and just letting it warm up a little bit. And then I'm going to turn up the accelerating voltage. And there's our vertical beam. And now we want to deflect it into a circle. So I'm going to my low voltage power supply and putting some current in the Helmholtz coils. And now let's put some magnetic field through the tube between you and me. And there we go. The magnetic field is bending the electron beam into a rather lovely circular path. So I've zoomed in a bit so you can see it a little bit better. So there's our vertical beam forming as the heater warms up. And now let's turn on the magnetic field. And there we go. The electron beam bent into a lovely circular path. And as we increase the magnetic field, that circular radius will get smaller and smaller and smaller. Now, the magnetic field's not exactly at 90 degrees to the axis of the tube, so I can see we're getting a little helical shape here, but it doesn't matter. It's a reasonably good circle. So whilst we've got this working, what's this got to do with the charge-to-mass ratio of an electron? Well, the charge on the electron wasn't known. The mass of the electron wasn't known. Millikan came along and did some work on the charge on an electron, and bending it into an arc allows us to calculate the charge-to-mass ratio. So if we know the charge on the electron, we can then work out its mass. And the way we do that with this piece of apparatus is we need to really know two things very specifically. We need to know the magnetic field strength due to the Helmholtz coils. That can be calculated. It's not a particularly easy thing to do, or it can be measured with something called a Hall probe. And we also need to know the radius of this circle that we've made. Now, the radius will change depending on how fast the electrons are going. So the other thing we need to know is the accelerating voltage. And if I reduce the accelerating voltage, you can see the effect is such that the electron beam changes the radius that it has. So what I'm doing now is reducing the accelerating voltage and increasing the accelerating voltage. So there's a lot of physics in this experiment, and it's not particularly easy to understand. But remember that electrons, when they're traveling in a magnetic field, feel a force at 90 degrees to the direction they're moving and 90 degrees to the direction of the magnetic field. It's a bit confusing because if you're familiar with left and right hand rules, remember electrons are negative, so they are going from a region that's negative to a region that's positive. So remember that the current is in the opposite direction, and that's a mistake a lot of people make. Few other bits to notice. Did you notice how the radius of the ring that we made got bigger and bigger as we turned up the accelerating voltage? Well, if you think about it, what's going on here is the electrons want to go in a straight line. They're being forced into a circle, so they're feeling a centripetal force, which is equal to mv squared upon r. And if they go faster, you're going to need a bigger force to bend them into a circle. So if we turn up the accelerating voltage, they're going faster, but we haven't turned up the magnetic field, so they will form a circle of a bigger radius. Now, it's the magnetic field that forces them into a circle, so if the centripetal force is mv squared over r, that must be caused by the magnetic field, which is BeV, or BQV if it's not electrons. Okay, so let's look at this a little bit more mathematically. So we know that the path of the electrons is circular. So I'll just draw their path here. And the other thing that we know is that they feel a centripetal force. So a centripetal force acts directly towards the centre of rotation. So that's that force there. And you'll notice the electrons are going tangential to the circular path they're taking, or at least they're taking a circular path, and we'll take a tangent there, and so the force is at 90 degrees to that. I don't want to go on for too long, but if the force is at 90 degrees, then it doesn't do any work on the electrons, and if it doesn't do any work on the electrons, it doesn't speed them up. It keeps them in a constant velocity going around in a circle. So this centripetal force will be caused by the magnetic field, and the magnetic field strength affects how strong that magnetic field is, but the centripetal force, of course, is also equal to mv squared upon r. So what we're going to do is we're going to equate the strength of this force caused by the magnetic field to mv squared over r, and we can use that to then work out the charge to mass ratio of an electron. So we know that the force that a charge feels when moving in a magnetic field is BQV, but I'm going to write that as BEV, okay, because B is the magnetic flux density, E is the charge, it would be Q normally, small q, but it's the charge on the object that's going around, and because it's an electron we'll use E. Granted, the electron's charge is actually minus E, but that's not going to cause any problems here. And the force also depends on the velocity they're moving at. Now be very careful here, I've tried to draw a small v, that's the velocity. But we also know that that force is a centripetal force, and we know from normal mechanics that the centripetal force is equal to mv squared upon r. So the mass of the object that's going around, we'll assume an electron rest mass for the sake of this. We won't consider any relativistic effects. V here is the velocity that's moving at that point, so I'll put a v here, that's the v of the electrons, being careful to remember that's a small v, velocity, and r is the radius of the orbit they're moving in. So I'll just put a little r here. I won't put any arrows on, but we know that r is the radius of the orbit. So what we need to do is play around with this equation to get the charge to mass ratio from it. So you'll notice we've got a v here and a v squared there. So let's just simplify things a little bit. B, E, and whenever you write this, always remind yourself, what do these letters mean? So the magnetic flux density, the charge on the electron, is equal to mv upon r. And then you'll see in a minute why, but I'm now going to move the E and the R. So we're going to end up with BR is equal to mv upon E. Okay, so now it gets a bit more interesting. You'll notice we've got V of the electrons in here. And the important thing is, where did these electrons get their velocity from? Well, they got it from the electron gun. And the energy they gained moving through a potential difference is EV. So that's the charge on the electron, and that's the potential difference, big V, that they move through. But we know that the energy they've gained is kinetic energy. So that's going to be equal to a half mv squared. Okay, be careful again, that's a small v, so that's the velocity of the electrons squared. Now, what I'd like to do is I'd like to substitute in here using this equation. So what is v, knowing what we know about the electron gun and the energy gained by the electrons moving through a potential difference? Well, if we rearrange this, the velocity that the electrons will come into the circle with, and remember, no work is done on them once they're there. They've left the electron gun. They've left the electric field due to the electron gun. Their velocity will be equal to root 2e v, big V, divided by m. So let's now substitute in root 2 ev over m for the velocity that we've got here, remembering that that is a voltage. So here we go, we've got BR here, and that's going to be equal to m upon E. Okay, that looks a bit awkward. We wanted E over m, but never mind. We've got the mass to charge ratio. So you'll see where I'm going with this in a minute. Now I'm going to substitute in this slot here for the V there. So BR is equal to m over E, and then root 2e big V voltage divided by M. And again, whenever you do this, keep trying to remember what do all these letters stand for. And I'm going to say it again, don't confuse this V here. This V is a potential difference. Okay, it's at this stage that students kind of go, well, why are you doing this? Just see what I'm doing and follow through. And it's one of those things you sort of have to learn, really. It's a way of manipulating this equation so you get what you want. So I'm going to put the m over e inside the square root. So to do that, I'm obviously going to have to square the m and square the e. So BR is now equal to root, and there's a whole lot in here now, 2e capital V over m multiplied by m squared over e squared. And I've got a good reason for doing that, and I think you can probably spot what it is. Okay, so we've got the e's here, that's the charge on the electron, and the masses inside the square root. So that allows us to go BR is equal to root, and then 2. See what happens to the e's here. Okay, so this e goes. So we've got 2v. Then we've got m squared over m, so that leaves an m. And then because we lost an e here, over e. Right, things are beginning to look a bit better. I'm going to move over here on the piece of paper, so just follow me through on this. Let's get rid of the square root. So let's square everything. So we've got b squared r squared is now equal to 2, capital V, the potential difference, m over e. And you'll notice there we're beginning to get another sign of the charge to mass ratio, or in this case the mass to charge ratio for the electron. Right, it's not rocket science now. We've got m over e, that we're looking for e over m, of course. So let's get rid of the 2v. So we've got b squared r squared is equal to m over e. The 2v goes this way. So there's the 2v. And as I always say, just remember what all these letters stand for. And this v is, of course, large V. It's the potential difference. So we're pretty much there. We've got the mass to charge ratio of the electron. So all we need to do is take the reciprocal of this side and of this side, and we've got the charge to mass ratio of the electron. So success is within our grasp. I'm going to swap sides on these because it's the charge to mass ratio we need, and also reciprocal both sides. So E over m, the charge to mass ratio for an electron in this experiment will be twice the potential difference that they were accelerated through, divided by the magnetic flux density squared multiplied by the radius of the orbit squared. Okay, so let's see if we can get the charge to mass ratio of the electron from our data. Now, I may be stating the obvious here, but don't go hunting for what is the mass on an electron or what is the charge on an electron. The whole idea about this experiment is we didn't know anything about this particle. So we fired it into a magnetic field, looked at its circular pattern, and then we can calculate, knowing only the accelerating voltage, the magnetic flux density and the radius of the orbit, what its charge to mass ratio is. It doesn't tell us what the charge is, and it doesn't tell us what the mass is, but it gives us an idea of what the ratio of those two quantities are. And then later on, we can do experiments to try and find out what the charge is, and then we can work back to the mass of the electron, but that's for another video. Right, we need our data here, and I'll write it down on this side. So the accelerating potential difference that we used was 150 volts. I'm not doing an error analysis here. I know I should, but I just want to speed things up a little bit. So I'm not going to go 150 plus or minus 6 volts or what have you. That's probably something we can do when we have more time and not in a video. The magnetic flux density. Okay, now this is tricky. because we didn't measure it. We didn't have a Hall probe that was calibrated to measure it. But there's something clever with this apparatus. You can calculate the magnetic flux density of a Helmholtz coil and a pair of Helmholtz coils, knowing the current, etc., and their size. But these coils have been set up so they have a factor that helps us do that. So the factor is 4.17 times 10 to the minus 3, okay, times by the current you pass through the coils. Now, I won't go into this in too much detail, but that's sort of written on the apparatus, so it allows us as scientists to work out what the magnetic flux density is from these coils in Tesla. Okay, what current did we have? Well, the current was a quarter of an amp, 0.25 amps. And then we can calculate using this sort of correction factor here, or at least this factor, we can calculate the magnetic flux density of the Helmholtz coils. So that's 1.04 times 10 to the minus 3 Tesla. Okay, so you would never be expected to remember this number. It depends on the apparatus that the school or the university has. But you will be expected to see that it's in the order of milli-Tesla. So if you get the answer in Tesla, you know, just 1 or 2 or 3 Tesla, you know you've made a mistake somewhere in the mathematics. Do watch out for milliamps here as well. Okay, D, so the diameter from one side to the other of the orbit was 0.07 meters. And that means that the radius, we're being careful here to be in meters. Do I need to say this often enough? I make these mistakes, is 0.035 meters. So we've got everything we need now to put into our formula for E over M. So let's do our E over M calculation. So E over M is equal to twice the voltage, so 2 times 150 volts, all divided by, I might use a ruler for this one because there's rather a lot of numbers to come in here, the magnetic flux density squared. Okay, so that's our 1.04 times 10 to the minus 3. And don't forget the squared, something I do all the time. Okay, or put it into your calculator incorrectly. And that's all multiplied by the radius squared. So that'll be times by 0.035 squared. So you might have a go on your calculator now and see what you get for the charge to mass ratio of an electron. So I hope you agree with me. You would have had to have paused the video there, otherwise I've got ahead of you. E over M from our experiment is 2.25 times 10. Now here's where it gets interesting. To the power of 11, that's a very large number, coulombs per kilogram. Now, let's just very quickly look at that. Why is this number so massive? Well, what we're suggesting is that 1 kilogram of these objects would have an absolutely phenomenal charge. And knowing what we know about electrons now, and knowing their mass is very, very low, though granted their charge is very low, okay, we would need, or at least we would have a very large charge if we managed to get a kilogram of these very, 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 very light particles. So what I've done here is I've just put down the textbook value for E over M for the electron, and it's 1.76 times 10 to the 11 coulombs per kilogram. Okay, so you might go, well, what does that look like? Well, let's just quickly look at how that compares to our value. Now, granted, I haven't done a full error analysis here, but let's just compare these two. So we'll look at the error compared to the textbook value. Now, the nice thing here is this is 10 to the 11 and that's 10 to the 11, so we can forget those. We'll just look at the decimal in front here. So hours compared to the textbook, so 1.76 minus 2.25 divided by 1.76 times 100 is equal to 28%, and it's 28% too high, isn't it? Okay, I was sometimes taught if I wanted to do it this way around, there are other ways to do errors, but if I wanted to do it this way around, I was sometimes taught good minus bad over good times 100. Okay, now just before you switch off and go, well, this was absolutely useless, just remember what you've done here. This is a truly astounding experiment. You with me have managed to measure the charge-to-mass ratio. This is this microscopic particle with absolutely minute charge in a school physics laboratory with a fairly simple piece of apparatus. I think there's a Nobel Prize in it for us there. So considering what we did and how we did it, and particularly the fact that when I do these kind of experiments, I just kind of switch it on and have a bit of a play. I don't spend hours trying to get things as accurately done as I can. So in summary, I was going to say it's not that bad considering our B value, because it's quite tricky to get a good value of B, and we never quite know if we really got that right. And of course, any error there, we've got to double it because we've got B squared. And we've also got some errors in the radius that we measured, and a better tube, and there are ways of doing this of course, but a better tube would actually have a graticule inside it, so we could more easily measure the diameter and therefore the radius of the orbit, because again we're doubling the error because we've got an r squared in the formula. So finally, let's very quickly look at why this number is so high. Well, if you remember the mass of an electron, we're looking at the rest mass here, is a very small number indeed. The mass of the electron is 9.1 times 10 to the minus 31 kilograms. And the charge on an electron, so I'll change colours here just to make it a little bit clearer. The charge, we call it Q of the electron, is 1.6 times 10 to the minus 19 coulombs. Granted, it's a negative value, but we don't need to worry about that. Okay, so if you look at these two numbers, well, you can see where the 10 to the 11 comes from, minus 31 to minus 19. So we know what the charge to mass ratio is. So looking at the numbers that we now have, and we now know for an electron, we can see that it is an object that has a charge but a mass that is very, very, very small. So the ratio of the charge to mass, will be a very, very, very large number. So I hope you could follow me there and found that useful, and thanks for putting up with my dreadful handwriting. It's never good at the best of times, but trying to write underneath the camera and in the way of a tripod and things is a little bit of a challenge, but good fun nonetheless. So I hope now you understand how we can mathematically analyse the data that we got from our experiment in the laboratory to work out in the school lab the charge to mass ratio of an electron. So I do hope you enjoyed that experiment. These are lovely pieces of apparatus and not everyone gets to see them, or they don't get this experiment demonstrated to them. They get rather simpler things shown, just the electron guns. Anyway, I'll be making another video soon and I look forward to seeing you then.